Hello, hello, geometry students. Welcome to 10.6 Part 2, Surface Area of Pyramids and Cones. Some more terminology we'll be looking at here, and make sure you're using those extra examples in your book to help you do this lesson. For this one, a pyramid and a cone, they're very related, just like a prism and a cylinder are very related. There's going to be now one base instead of two with pyramids and cones versus prisms and cylinders. So as we take a look at this, we would call this our base here. This is a net of a square pyramid instead. So this is a net of a pyramid, and it's a square pyramid because the base itself is a square. You could have a different kind of pyramid, like this could be a hexagon, this base could be a pentagon, this base could be whatever gon you want it to be. It would be a different kind of pyramid, but it would still be considered a pyramid. So a net of a square pyramid, we're going to be looking at this as we develop the formulas for the lateral area and surface area of these things. And then over here, the pyramid itself, the three-dimensional figure, this is going to be referred to right here as the base. We'll use capital B once again, as we did in the previous lesson, or the 10.6 part 1 lesson, to denote the area of the base. So the base right there. Lateral edge is going to be, so before we talk about lateral things kind of being around it, around the base, as you circle around the base, the lateral parts in this case will always be triangles instead of rectangles. For prisms, it was always rectangles. For pyramids, it's always going to be triangles, because the pyramid will be just having one base, and all those edges, these lateral edges we call those, once again, they'll meet at a single point. We call that single point the vertex right here. This is the vertex of the pyramid, where they all come together. This right here, this red dotted line, from vertex to the center of the base, assuming these are regular polygons down here, this one happens to be a square, which is just a regular quadrilateral. This is the height, or you could even say the altitude once again, but the height of the pyramid there. And then you have a lateral face would be this part. So this triangular part would be a lateral face. This would be another lateral face. And the back from there to there to there, that's the back lateral face, and then there'd be one more on the left side here. So this is an example of a lateral face. And I think I've got everything there except for this that I wanted to talk about. So that was your base. This part here is the height of the triangle, but in terms of the pyramid, it's kind of the height on a slant. So we call this the slant height of the pyramid, but it's the height of one of the lateral faces, which are all triangles. So the slant height, and we often refer to that, and I really don't know where this came from or why this gets used, but a cursive L, cursive lowercase l, is often used to denote the slant height of something. So if you take this pyramid, unfold it, you get this net for that pyramid, and right here would be the slant height once again. So L for the slant height, that's this one right here. This red length here is the same as this blue length over here. So if we are thinking about the formula for this thing, so I've taken this, made a copy of it, put it down here to be able to discuss that and where this formula comes from. If we were to find the area of all four of these triangles separately, and then put the sum of those things together, that would be the lateral area, be the area of all the lateral faces. So you could do 1/2 base times height for each triangle. So 1/2 of the side length of one of these sides of the bases times the slant height for each triangle. But if you did perimeter, you would do all four bases at the same time. So you could do 1/2 times perimeter times height, and it would give you all the lateral faces simultaneously without having to do 4 separate calculations. Or if this were a pentagonal pyramid, 5 triangular calculations, or a nonagonal pyramid, 9 of them. I don't want to do that if I don't have to. So if you do 1/2 perimeter times slant height. That's the same in effect as 1/2 base times height for each one of these triangles all at the same time. So the formula for lateral area of a pyramid, given that this is the slant height right here, so it's from the midpoint, assuming this is a regular polygon again, midpoint of the side to the vertex, we call this cursive L for slant height, and then this is your base. The lateral area would be the area of just the 4 triangles together. So it would be 1/2 base times height for each triangle. But if you do 1/2 perimeter times slant height, that's 1/2 base times height for each triangle all together, all at once. So that is the formula that you would use here. This is the area of all lateral faces. It's all of them put together at the same time by using perimeter, capital P there. And then surface area is going to be the same sort of thing. So we're still going to use the lateral area, and we'd have this. Whoa. Let me try to erase that. I just pressed a button on my pen that I'm writing with here. So we'd have, this is our slant height still. We'd have lateral area. Plus now, instead of with prisms we had 2b, now we just have 1 base. So it's just going to be plus b. But then I think the best way to write this, or the most frequently way you would write this, would be to replace LA with 1/2 perimeter times slant height plus the capital B. So P standing for perimeter of the base, L standing for slant height, and B standing for the area of the base, just like it was in part 1 of 10.6. So from there, we've got our formulas. We're going to take these formulas and make use of them in some example problems here. So welcome to Egypt, probably the most famous pyramids in the world, square pyramids at least. So we've got that as a real life example. I'm not saying these are the Egyptian pyramids, but example 2, this one a much smaller pyramid. So 20 centimeters for the slant height, 15 for an edge length, and assume that these are square pyramids. Unless you're told otherwise on these kinds of problems, assume that the bases are regular polygons. So we've got 1/2 perimeter times slant height would be the formula I would use for lateral area. Over here, it's lateral area plus base, which could be replaced with 1/2 perimeter times slant height plus area of the base. So we're going to use that formula for lateral area. We're going to add the base. There's only one of them, so not 2b like the prisms. It's just a single b for pyramids. So let's focus on this problem until we arrive at the answer, and then we'll go back to that problem. So 1/2 perimeter in this case. Perimeter of the base, this is your base, would be 15, and if you can assume these are regular polygons like I had mentioned a little bit earlier, you can assume that would be 15 plus 15 plus 15 plus 15, or you could just say 15 times 4. And then the slant height is 20. So this information all was directly given to you basically, except for perimeter. You just had to recognize it was that times 4. So you'd have 60 for that, 20 for that. Half of 60 is 30. 30 times 20 is 600. You've got 600 centimeters squared for the lateral area for example 2, part A. And then part B, the lateral area plus the base becomes 1/2 PL plus B. So in this one, perimeter is going to be 16 times 4. You can assume this is a regular polygon once again. And then slant height, on this one, this is your slant height. You are told the height of the pyramid, but not the slant height of the pyramid. But if this is 16, and we're assuming this is a regular pyramid, there's nothing that's oblique or slanted in any way about that. Safe assumption unless you're told otherwise with these kinds of problems. If that's 16, then from here to here would be 16 as well, and then this would be the midpoint of that. So that would be 8 right there. So that is a safe assumption right there. Let me get off of that menu. I'm not sure why it went onto that. And then so from there we could do some Pythagorean theorem work right here. We've got this right triangle, this green right triangle. We could say that 8 squared plus L squared, slant height squared, equal, I'm not saying that right. 8 squared plus, the L should be the hypotenuse. So 8 squared plus 24 squared equals L squared. That'd be 64 plus 5, 76 equals L squared. So that means L squared would equal, I'm just flip-flopping the order in which this is written, would equal 640, and you could take the square root of both sides to get what L is. And I'm going to leave it exact for now. I'm going to leave it as square root of 640. If you were going to round that off, I would want you as one of my students to use 5 or more decimal places so that your answer isn't rounded off so much midway through the problem that it makes your final answer off by even more. So I'm going to use, though, this for now, the exact value there. Excuse me. And then the area of the base, well, the base is just a square, so it's a special type of rectangle. You can just say that would be base times height, or 16 times 16. So from there, we'd have 1/2 times 64 times the square root of 640, plus this would be 256. Half of 64 is 32, so you'd have 32 times the square root of 640 plus 256. Now, if this kind of problem said to get this in simplified radical form or an exact answer, we could try to take out what we could out of there. So why don't we do that a second? This would be 32. And then you could use a factor tree to do this. I'm not going to take the time to do that here because I'm noticing what the biggest perfect square is here. It's 64. 64 times 10 would be that. But if you split this up, did a factor tree, and took out what you could, you should get the same thing as what you see here. This 64 can come out as an 8 because the square root of 64 is 8. And you'd still be left with a 2 times 5 on the inside, which would be 10 if you did the factor tree way. So plus 256. This ends up being, so 32 times 8. 30 times 8 is 240. 2 times 8 is 16. It looks like we'd have 256 times the square root of 10 plus 256. No units are given on this one, so you could say just units squared or leave it like that. So this would be an exact simplified radical form answer. These are not like radicals, so we couldn't put those together. But if you were allowed to round, really you could have stopped right here, or even just had the first line and used a calculator to do all the work for you. Show me the setup if you're one of my students, and then go right to here. I'd be okay with that if it said rounding was okay. So 1065.5 units squared for that answer right there. So then part C, I've got a quote. I feel like a lot of quotes are from Einstein, and I'm occasionally skeptical that Einstein said everything that people attribute to him, but I thought this was a good one, and I feel like this could have come from Einstein for sure. So solutions to tough problems should be made as simple as possible and no simpler. I feel like this problem, that definitely applies. This is going to be a tough problem, perhaps the hardest problem we've done, not just in this lesson, not just in this chapter, but perhaps all year. This is a very challenging problem. I've got a whole slide of room for it here, a whole slide's worth of room. So let's check it out. Let's dive into this problem and make the solution as simple as possible, but no simpler. So we've got the height of this, and we have a lateral edge. That's what I'm referring to here as 10. So 10 is the length of this lateral edge right here. For the formula for a surface area, we need, and let's write it out, and let's figure out what we need to figure out from there. So we need lateral area plus base. Lateral area can be replaced with 1/2 perimeter times slant height plus the area of the base. So on this one, the area of the base is going to be the area of this pentagon. So that's going to take some work. Pentagon doesn't have an easy way or an easy formula. We have to use that 1/2 perimeter times apothem, or calculate the area of one of the little triangles of the base and multiply it by 5 in this case. That's the approach I'll take here. And then 1/2 and then perimeter of that, well, I don't know the side length yet, so I'm going to need to figure that out. And then the slant height, I also don't know that on this one, so I'm going to need to figure that out. So on this one, I'm going to draw, and I'm going to color code. I think you'll find that very helpful. I'm going to try to draw as neat as I can here with this pen. It's a little challenging to draw not as neatly as I normally could with this pen, but I think that should be pretty good there. So I'm going to be looking at this green triangle to try to figure out this slant height. I'm going to be looking at this red triangle from here, here, and here to try to figure out some information initially though. So I know this is a right angle here in this red triangle, which is sharing a side with this green triangle right here. This is 8 in the red triangle. It's also 8 in the green triangle. So if I look at the red triangle, I'm going to draw some separate stuff here as I go through. So this is 8, this is 10 in the red triangle, and then this would be this length right there. And then eventually I'm going to look at what I'll call the blue triangle, one of the triangles of this pentagonal base. So I've got the red triangle, the green triangle, and the blue triangle. And I'm going to start with the red triangle. So I know, let's call this x right here for ease of reference. This would be x squared plus 8 squared equals 10 squared. So Pythagorean theorem being used here for that. This would be 64 and 100. If I subtract 64 from both sides, looks like I've got 36, and so square root of both sides, x would equal 6. That is useful to know. So then in my green triangle, I don't have new information yet on that, but it looks like in the blue triangle, I'm going to draw a picture of that here. I now at least would know in the blue triangle, which should be an isosceles triangle here. Let me try to draw that a little better. This would be the green apothem right there. That length would be this length right here. And now I know x. This was that red part. This is x equals 6. That's in this blue triangle right here. This would be 6 then over there as well. I could do this to figure out what this angle is right here. It's doing that again. Let me get it off of there. So this angle right here would be 360 divided by 5 split in half. 360 divided by 5 would be the area of this whole thing. Excuse me, and that's going to be 72, and 72 divided by 2 would be 36. So I've got a 36 degree angle right here, and then I'm looking at this triangle right there. I could call this, why don't I call this y, and then that would be y here as well. And I'm going to refer to this part as A for apothem. That would be this green length right there. And once I know what the apothem is, then I could use the Pythagorean theorem one more time to get what that side length or that slant height more specifically is. So if I do this, I've got 36 to figure out what y is. If I know what x is 6. This looks like a opposite over hypotenuse problem. That's sine. So sine of 36 would equal y over 6. That means y, if I were to put this over 1 and think of cross multiplying, most of my students in the past have found that a useful or easy way to see what that is. Y would equal 6 times the sine of 36. For now, I'm going to leave it like that. If you use a calculator and approximate it, not a problem at all. Just make sure you're using 5 or more decimal places if you're one of my students. If you round it off too much, it's going to make your final answer way off, or at least too far off to be an acceptable answer or an acceptable range. And then cosine could be used in this blue triangle. Cosine of 36, if you think SOHCAHTOA, sine was opposite of hypotenuse. Cosine is adjacent over hypotenuse. So adjacent to this 36 degree angle would be this green side, the apothem. So you'd have A over the hypotenuse, 6. If you do the same thing as up here, you can multiply both sides by 6, or think of it as cross multiplication. A, the apothem, would equal 6 times, not the sine, but the cosine of 36. And so from there, now I can look at the green triangle. I've got that y is 6 times the sine of 36, I will want to use the fact that I'll call this s for side length, that s would equal 2y, so that means s would be 2 times 6 sine of 36, which would be 12 times sine of 36. I'm going to use that information later on as well. All three of these blue things that I'm circling here you could approximate to, let's say, 5 or more decimal places if you're one of my students. And then from there you could plug stuff in. So surface area, I don't have perimeter yet, but I can figure out perimeter by doing the side length, which is this, times 5. If you approximate that in a calculator, plug that in. If you didn't approximate it, left it like this, you could just write 5 times that. 5 times 12 times the sine of 36. Not the sim of 36, the sine of 36. There we go. And then slant height, still an unknown, still something I'm trying to figure out. In the area of the base, I've got everything I need for that now. I'm going to be doing the 1/2 perimeter times apothem, or 1/2 base times height to get one triangle, and then multiply that by 5 triangles for the whole area of the base. So slant height, I am almost there. I've got what I need. I'm looking at the green triangle now in that original picture. This is a known quantity. This is A, that's the apothem. That's this part right here, that's the apothem. So the apothem is this part. This is A, which is 6 equals 6 times sine, 6 times cosine, sorry, right here. So 6 times cosine 36 degrees. And then the height is a known quantity. That was 8. That was given to us right here, the height of the pyramid to start. And so this is our slant height. This is our L. And so to figure out what L is, it looks like I could do 8 squared plus A squared equals L squared. And so from there, I'd have 64 plus A squared equals L squared. And that means L squared, if I take the square root of both sides, why don't I just do that now, get rid of the squared part then. L, oops, get my green back. L would equal the square root of 64 plus A squared, but A squared I could replace with that thing squared. I'm going to show you at this point, I did do some calculator approximations for all these things. At this point I've got, I have these to 4 decimal places. Let me get it to 5 decimal places here. And so A, 6 times the cosine of 36, approximately 4.85410. The side length being what you see there, 12 times the sine of 36. Oops, I'm just typing that into a calculator quick here. I did not have that value written down already. Sorry about that. So 12 times sine of 36, 7.05342. And then y being what it is, I could show you that approximately as well. So 3.52671 right here, 3.52671. So I've got all these things approximated. So basically, right here, A squared, if I take this value and square it, I'm going to keep it in the calculator. So I'm going to take 6 times the sine of 36 and square that value. And it looks like I would have, this would be plus, so A squared gets replaced with this value squared going in right there. And that would be 12.4369 for that. So L is the square root of that, which is approximately 9.35747. And I just realized, and you're probably seeing me doing the pause buttons over here, I just realized I wrote the wrong thing down here. That was 6 times the sine of 36 squared, not 6 times the cosine of 36 squared, which is what I should have had. instead. So let me rewrite what that should be. So 64 plus, and then I'm getting 23. If I take 6 times cosine of 36 in a calculator, get that decimal approximation, square it, plug it in here, I've got 5, 6, 2, 3, 1 approximately. So that looks like it's going to be 87 and some change. So the fact that it's a little over 9 makes sense. Square root of 81 would be 9. So the square root of 87 and some change would be a little bit more than that. So I'm getting, for that, 9.35747. 9.35747. That is my slant height. Took some definite work to get there, but it's stuff you should know from before. Pythagorean Theorem twice, and then some trig to get your values there. So to plug in then the slant height, I've got, I could say what I've got here, or I could have rounded it off as well. I'll do that in the next step. So 9.35747 plus, and then the area of the base. If you prefer the formula 1/2 perimeter times apothem, if you learned it that way, go ahead and do that. If you've learned it as the number of, or the area of one triangle, I'm going to say one pentagon triangle times the number of triangles. That's the way I had taught it earlier in the chapter 10 notes here. So if you're doing that, you could take this and call that 60, 5 times 12, 60 times the sine of 36 degrees, and this would be 9.35747. And the area of one pentagon would be the formula 1/2 base times height. One pentagon triangle, rather. You've got, if I were to split this up, I've got 5 of these blue triangles here in this picture. So find the area of one of them, multiply it by 5, and had the area of the base by doing that. So 1/2 base times height would be 1/2 this side length S down here, which I calculated as this, which was approximately this. So 1/2 of base, 7.05342, times the height of the blue triangle, which is the apothem of this triangle right here, or this pentagon. Apothem of the pentagon is the height of that. So I could plug in this right here, 4.85410. And then this, I should have been using a squiggly equal sign along, because it has been approximated at this point. 60 times the sine of 36 is about, and so I'll have everything in a decimal form at this point, 35.267 I'll throw in an extra decimal place there. So I've got that to 6 decimal places. I've got this to 5, and I'm just going to keep it like this. I would not expect you to try to write out or do any more math on that besides just plugging that all into a calculator and letting it do the work for you. So if you take all this, multiply it through in a calculator, definitely double check me on this and make sure that you're getting the same thing as I do here. But I'm getting 250.6, and there are units included on this. So meters is units that are included, that are in the problem up here. So this would be 250.6 meters squared. And I just realized after double checking, I left something off here. So I apologize. I felt like I could have done a better job on this one, but I also am doing all of these in one take, so it's a little more challenging that way. So 1, 0, I forgot to multiply by the number of triangles. So I should have multiplied that by 5. So I should have a times 5 there. With that in there, then if you multiply all this through on your calculator, then you have 250.6 meters squared. Solutions to tough problems should be made as simple as possible and no simpler. I don't see a simpler way to do this one. I don't think you'll see one this hard on the test. This one was meant to be a challenging one just in the notes, though, to kind of see if you could put everything together on this one with me. So let's take a look, though, at cones now at this point. They're essentially the same idea as pyramids, just like cylinders are the same idea as prisms, but you're just applying the formula in a circular sort of way instead of, or you're thinking of perimeter as circumference instead. So if I think of this lateral area of a cone, I'm thinking of around it, not including this base, not thinking, I am thinking about the radius, but that will be involved in here somehow, but I'm not going to add the area of the base when I'm all done. So this surface area is going to be lateral area plus the base, but I need to know what that lateral area part is. So it's going to be something else that I'm filling in there. So let's go back to the idea back here, going back to this. We had 1/2 perimeter times slant height. The idea is or should be the same because the base becomes a circle, but it's still meeting at one point. The lateral area could still be found by essentially taking an infinite number of tiny little triangles on here and making infinite number of these tiny little triangles all the way around this thing, finding the area of all those triangles, adding them all up. But if we did perimeter of the circle, so I'm thinking back to 1/2 PL here. If I think of the perimeter of this, that's going to match up with this part right here. The circumference is the fancy word for a perimeter of a circle. So if I measured from here and wrapped around the circle and went to there, that length is going to be the same as it is from here to here on this lateral part of the cone. So I could replace P with 2 pi r with circumference and then L. And so if you multiply that together, the 1/2 and 2 cancel, and pi r L is the slick formula that works for lateral area of a cone. So pi r L, L is going to be, once again, your slant height. So in this case, the slant height is the lateral. There really is no edge to it, but it's the lateral length from there, from the vertex to any point on the circular base. And same thing would work over here. Lateral area can be replaced with pi r L. In the area of the base, there's just one of them, so there's no 2 out in front like there was with a cylinder. It's just a single pi r squared. The area of one circle is pi r squared. And so those are your formulas that you'll use for lateral area and surface area of cones. So for part A of example 4, we've got lateral area only that we're calculating here. Lateral area would be pi r L. This one should be pretty straightforward. It looks like we've got pi times 6 times 10, very straightforward, very simple in terms of a lateral area formula usage of the formula for cones. So we've got 60 pi. If we multiply that together, inches squared would be my units. That's an exact or pi form, and then approximate form for that would be 188.5 inches squared to the nearest tenth. So rounded form to the nearest tenth, exact form, pi form. If we do lateral area once again, this is pi r L. This would be pi times 5.7 is the radius. L is unknown on this one, but I'm going to label it with an L there. And it looks like 12, that's referring to this regular height of the cone. So this is going to be 12 squared plus 5.7 squared equals your hypotenuse squared, L squared. This would be 144. And this would be 32.49 equals L squared. That means L squared would equal the sum of those two things, 176.49. And then if we take the square root of both sides, we'll have our value. And I'm going to approximate this. I'm going to leave it exact actually for now, and then let the calculator do the work in the final step. So this is exactly the square root of 176.49. Take that value, plug it in up here, and write it just like you see it there, 176.49. And so this would be approximately, in a calculator, pi times 5.7 times that, 237.9 centimeters squared. You could call this as well 5.7 pi times the square root of 176.49 centimeters squared. That would be an exact pi form, radical form answer, but I would not expect you to have to write something down like that with decimals, with radicals, and pi form. Most likely going to ask you for a rounded to the nearest 10th answer on something like that. I think we've got a couple more problems here. All right, a couple more examples split into two different parts. So surface area of the cones now. Now we're looking for surface area. We're going to include the base, include the pi r squared part, include the area of the circle at the bottom. So we've got, I'm going to go straight to the more specific formula. It's lateral area, which is pi r l, plus the base, which is pi r squared. Writing out that formula in general first. I think that's always your best bet with these kinds of problems. And then plugging in what you know to calculate what you don't. This is going to be pi times 5 times 13. That stuff is directly given to me there. Radius is 5, slant height is 13, plus pi times 5 squared. This becomes 65. So you have 65 pi plus 25 pi, and this would be 90 pi. Combine like terms, meters squared for your units. Put that in a calculator, you'd have approximately 282.7 meters squared. And then on this one, it looks like you're given the diameter, so that's d. So then you divide by 2, and you can get the radius as 0.6 feet. So the radius is 0.6 feet, your height is 2, and so if your height is 2, your slant height would be this part. You don't know that yet, but you have this part is 0.6, 0.6 right there. This part is 2. You could figure out L from there. So if I look at this red triangle right here, I would be saying 0.6 squared plus 2 squared equals L squared. This would be 0.36 plus 4 is L squared. That means L squared would equal 4.36. And then take the square root of both sides. You'd have L is, and I'll keep it exact for now, the square root of 4.36. So we take that, and we take our surface area formula, which is pi r l plus pi r squared. And we're going to take r, plug it in right there, and right there. And we're going to take L and plug it in right there. And so if we do that, it looks like this. Got pi times 0.6 times the square root of 4.36 plus pi times 0.6 squared. And so you'd have 0.6 pi times the square root of 4.36 plus 0.36 pi. That squared is 0.36. Definitely wouldn't expect you to leave it in that sort of form. We would take that, put that in a calculator. You honestly could take this step right here, put that into a calculator, skip this, and go right to this from there to get 5.1 if it said rounding was okay. So 5.1 feet squared to the nearest 10th on that one. So one more example to do, and 10.6 is wrapped up part 2 from there. Yeah, there's your terrible math joke for the day. Example 6, solve for the requested information, rounding answers to the nearest tenth. So it's specifically saying how to round on this one. We've been rounding to the nearest tenth on most of these, but just be careful you're reading and following any directions. So surface area of the cone, its height is 16 inches, its slant height is 18 inches. So I think it's valuable to draw a picture on this one. So I'm going to draw a cone. And I'm thinking of the radius is unknown. I'm going to call it r. My height is a known quantity. It is 16 inches. And the slant height right here would be 18 inches. So it looks like a Pythagorean Theorem problem initially to figure out what r is. So you've got r squared plus 16 squared is 18 squared. That means r squared plus 256 is 324. You can subtract 256 from both sides, and you're left with r squared that'd be 68 then, and you take the square root of both sides, and you'd have r is the square root of 68. I'll leave it exact for now. Best to leave it exact as long as you can. The surface area is what's requested. That's going to be the lateral area, which is pi RL, plus area of the base, which is pi r squared. We'll take this and we'll plug it in. Up here we'd have surface area is pi times the square root of 68 times 18 is your lateral, your slant height rather, and then plus pi times, and I'm going over a little bit here, but square root of 68 squared. This square and square root would cancel, so you'd be left with 18 pi times square root of 68 plus, and then just 68 pi. And 68 would be, if you tried to break it down factor tree style, you'd have 2 and 34, you'd have 2 and 17. So you could take out a 4. If you had to get this in an exact form, you could be writing this as 18 pi and then 2 times 2 times 17. 17 is prime, so you couldn't do anything more with that. You could take out the 2 times 2 as a single 2, so you'd have 2 times 18 pi times the square root of 17 plus 68 pi, and then that would become 36 pi times the square root of 17 plus 68 pi. Unlikely that you would be required to do that, and it even says rounding to the nearest tenth here, but I'm just showing you the process. It said give an exact value. So you could go right from this to the answer, or at least right from this step to the answer, and be totally justified, totally safe, especially seeing the directions here say what they say. So this would be 679.9 inches squared. And then finally, the surface area of a cone when it's known on this one. So this one we're going to be replacing SA with an unknown quantity. The radius is 6.1. We're trying to find the slant height. That's our unknown on this one. So I'll draw another picture here, a sketch to help us see what's going on this one. So a cone, this one we know the radius is 6.1 and 6.1 feet to be specific. This is slant height, that's your L part, so we're looking for that. It does not tell us what the height is either, but we may not even need to know what that is. But the whole surface area is right here, 293.2. So let's take our formula, write it out in general, and then plug in what we know to find what we don't. So we've got pi RL plus pi r squared. Replacing this right here with 293.2. R is 6.1, L is unknown. R 6.1. And so from there, 293.2 would equal 6.1 pi times L plus, and then 6.1 squared would be 37.21. And I've got that times pi. So from there, if I were to, there's a couple approaches you could take to this. You could divide everything by pi. So start, and then make sure you divide that by pi. Or you could notice this is really just a decimal number. It's that times pi, which is just a decimal that goes on forever. Irrational number there. We could subtract that from both sides. So I'm going to subtract 37.21 pi from both sides. That would go away there then. This one, factoring not required because I don't have a squared variable part and a variable part after that. I just have the variable. Nothing squared I have to deal with like I did with a couple of the problems that I did in the 10.6 part 1 lesson. So we're left with this 293.2 minus 37.21 pi. You could take this, approximate it. One of my students go 5 or more decimal places and get what that is approximately at this point. I'm leaving it exact for now because then at this point I could take this whole thing, divide by 6.1 pi. I'm going to put it in parentheses though. If you are going to do this all in one step, make sure you put it in parentheses. Otherwise it's going to divide this by, or it's actually, if you do this all in a calculator, you have to put the top and the bottom in parentheses. Otherwise it would take this times pi, divide it by 6.1, and multiply that by pi, and then subtract that whole sum from 293. We want to do this all together, and then do that all together. So make sure you include those parentheses if you're doing it this way, all in one step. And then from there, you should get 9.2 as your final answer. So 9.2, and this would be, it is a slant height, so it's not going to be units squared or feet squared. It's just going to be feet. It's just a length at that point. And so from there, whew, we are done. That was a good lesson. I like the challenge of this problem especially. If it can get there, there we go. Of example 3, I find that I am quite certain that this one will go beyond the level of difficulty you'll be seeing on any test from me. But a very intriguing problem, puts a lot of stuff together. One of the harder problems, if not the hardest problem we've done all year so far. But these will be more like the ones you're seeing here. The ones besides example 3 will be more like what you would expect to see on a test for geometry in our class. Hope that was helpful for you. If you have any things that you noticed were wrong, besides things that I fixed midway through the video, like especially in this one, there are a couple things that I kind of had some hiccups on there, so I apologize for that. But if you see anything wrong, one of my students, send me an email. Anybody, feel free to comment on the video, and I'll get back to you on that. And appreciate you watching this and hopefully learning a little bit from it. If you're one of my students, hope you found it helpful. If you're somebody else just watching on YouTube, hope you found it helpful. I'll stop talking for now, and I hope you have a great rest of your day, whatever time of day you might be watching this. Catch you later.